Okay, so I have a request that once again, I just cover the RPM manifold pressure explanation as on when you don't move the throttle. So I don't know if I'll explain it any different than I did before, but we'll see what happens. So I'll let this be my manifold absolute pressure gauge. And then this one is RPM. And oh boy, I should have done this like hours ago. I just realized I could possibly do something. Let me see. Let me see if I can open something up over here. I may regret this decision. Okay, I'll let that open. So over here, what we have, the manifold pressure gauge. Yep, there we go. Okay, we're back. Okay, manifold pressure gauge and the RPM. Now, if I am actually running an airplane with the throttle, all right, just normal everyday operation, I get into the airplane and I'm going to have about 30 inches. Why is it over there? Everything just went to hell in the handbasket. I knew I should have done that. Stand by. Technical difficulties. We'll just edit this out. All right, everybody's back with me. I think I lost everything there.
No, I'm still here. I'm here.
I know, but the notes went away. Not that that's a problem, but okay. So, okay. So if I have, there we go, manifold pressure and RPM, manifold pressure, RPM. What I was trying to do, I have X-plane and I should have had it open already and running. I haven't opened it forever, and I can actually run an aircraft and let you guys watch me run an aircraft, which is really cool. And it would kind of show you how this works. So if I'm running an airplane normal on the ground and I'm not trying to adjust carburetors or anything, but just being a pilot type person and running an airplane, and I get in an aircraft, and before I start it up, I'm going to have, let me see if I can pull up some pictures. Let's see.
I've got one. I just can't figure out where my video is. Like when I start doing the video, I can't see what I'm projecting.
Oh, yeah. Okay, so this is an altimeter I just pulled up real quick because I wasn't prepared to talk about this. But this little item right here is called a Colles Min Window. It's called a Colles Min Window. And you'll get this later, but if I am right now, this is 29.92, right? And we know that 29.92 is the standard day. So if it was a standard day, and right now this is showing 180 feet. So there's 100s, 20, 40, 60, 80. So if it was a standard day and I turn this little knob over here and it says 29.92 and this says that, and that means I'm at that altitude for a standard day. So let's say I'm at 180 feet. So I dial in 180 feet. I move this till it says 180 because that's where I'm at, right? So if I was at McClellan, it's 74. So I would dial this until the needle was over here and I would read this. This is how you know what your barometric pressure is, by using an altimeter, right? This is how a mechanic does it. So if I know I'm at 180 feet, I'm going to turn this little knob here and that moves these dials. And this dial would move around and I would stop right there and I'd say, okay, that's 180. Now I would look at this and go, okay, my pressure outside is 29.9. 2, 4, 6, 8, so that's 29.92. And I go, okay, so right now my pressure outside is 29.92. And then I would look at my manifold pressure gauge and the engine's not running. And, I'd have 29 and 30 and it would be right about there, about 30. And I'm like, oh, okay, my manifold pressure gauge is correct because the engine is off. And of course, right now my RPM would be at 0. So I start the airplane up and I take it to an idle. And let's say I'm an idle at 700 RPM. So I'm idle at 700 RPM. Now, because the throttle valve is closed, it is closed on the carburetor, there is going to be a tremendous amount of suction on this thing. And it's going to be way down here. I think about 14. I'm just going, so it's going to be way down here. That's suction. So really anything from here to here is like a suction, and anything from here to here is actually higher pressure in the manifold. So, all right, so I'm all the way down here and I'm running it. And as I advance the throttle and I open up the throttle valve, the black knob, this is going to go that way, and this is going to go that way. All right, and this is going to go, say I go all the way up to red line, which is 20, we'll say it's 2,500 here, just to make it simple. It's like all the way up to 2,500. This thing is going to probably go all the way up around to 29 inches. All right, and it's not going to go to 30. And I told you it'll never go all the way up unless there's a turbocharger, because there are restrictions going through the carburetor, the air filter, and the venturi, and the throttle body part. They all kind of conspire to rob about 1 inch of manifold. So this is going to end up being about 29 inches at 2,500 RPM. Okay, so that's great. So, all right, and that's what it's going to look like while I'm running the aircraft. But now let's do all this again. And now we're going to go back. We're going to say, okay, we're actually going to show you what it looks like when you're messing with this on our ground power unit. And it's the same thing. It's got a manifold pressure gauge and it's got an RPM, and you're going to start it up, and I'll say, well, let it idle right about 700 RPM. So, all right, so you take it, you have it idling at 700 RPM, and we look over, and I'm trying to remember what the manifold pressure was on that. Let's see if I can, let me see. I had a gauge in front of me. There we go. Where'd it go? Oh, that's not a nice one. That did not open very big. So here's a manifold pressure gauge. Ours looks very similar to that you're going to be using. And so we'll just use the same numbers. So we've got it, and I don't remember what it is exactly. It's around 14 or 15. So we started up and we're idling it right here. All right, so we got 14 inches and 70 RPM. Now, if I mess with the throttle, it's going to act just like I told you before. The RPM is going to go up and the manifold pressure is going to go up, because that's what they do when you open the throttle. But now we're not going to open the throttle. We're going to lock the throttle. We're going to safety wire it, weld it, use hose clamps, and put some rope around it. So there's no possible way the throttle will move at all. It is locked. Everybody follow me? Welded, shut, can't move it, frozen solid. But if I mess with the mixture control, I can make the RPM go up and I can make the RPM go down simply by making it too rich, too lean, best power. So if I have we'll say I screw the mixture all the way in. So if it's all the way in, that can be rich or lean?
Lean.
Yeah, it's going to be very lean. It's going to be blocking off that little passage. So it's super lean. Okay, so I've got it all the way in, which is lean. Okay, so I'm going to start backing it out. And as I back it out, I'll make a chart here. So we'll back it out. This will be in, this will be out. Okay, this will be then lean, and this will be rich. And this can be RPM. So will that work? RPM, high, low. Let me think about that. So that may not work. Oh, I should have done it. I know. All you gotta do is just change it around. It'll make more sense to me, more sense to you. Let's try it this way. We'll let this be lean. Let this be rich. That makes more sense. This is RPM. High and low. RPM. Okay, so if it's lean, we'll say it's going to run kind of low. And then as I back out that screw, it's going to go from rich. It's going to go from rich to lean. And so as I back it out, it's going to get, the RPM is going to slowly go up, slowly go up, slowly go up. And then it's going to start slowly going down, slowly going down, slowly going down, 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 down. What is this spot right here?
Best power.
Best power. All right. So here at best power, that is correct. That is best power. At best power, that is the highest RPM. Okay. Now, if I made another chart, this may or may not be a good idea, and correlated it, because it's, I would say this is map, this is low, this is high. Why? Because since I locked that throttle down, as this goes up, this becomes more of a vacuum. Because the air pump, the engine, is going faster, it's demanding more air, but it's not getting it because the throttle is closed. And so it becomes more and more of a vacuum. So they move opposite each other. And I don't know how else I can explain that. So, MJ, does that help?
Yeah, okay, so yeah, now I get it.
Okay. So just remember they're inverse. So high RPM is low manifold. I could, hopefully I don't mess anybody up. Instead of doing this, I could put vacuum. And we could say, well, it's a high vacuum and low vacuum, right? Because it means the same thing. High manifold pressure low means a high vacuum. So if I wanted to call it vacuum, I do the same thing. As this goes up, the vacuum gets more, which is higher. And as this goes down, the vacuum gets lower, which is actually a higher manifold. Did that help?
Yeah.
Yep.
So because it's increasing, you're moving more air, but it's still the same restriction.
Yes, exactly. You are moving more air, same restriction.
And because it's the same restriction, it's like
The vacuum's got to go up.
like the effect is like if the throttle was closed, kind of thing.
Because the throttle is closed. Yeah. Okay. Let's talk about automatic mixture control. Let's kind of mix that. All right. So some carburetors, some fuel injections, some pressure carbs, they have an automatic mixture control. Quite the add-on. You don't see that often in smaller carburetors ever, but it's very simply done. And this is it's the same idea as we looked at before with the manifold pressure economizer system. So all you have to do is take something of this nature and make it work for you. So what we have here is a sealed bellows, and it's sealed with an inert gas that responds to changes in pressure. The potato chip bag theory, it's all it is. In fact, and this is usually made out of a thin metal that is allowed to expand and contract. Just like a potato chip bag, I think that's some sort of metal anyway. So what happens here is this is then vented to whatever you want to vent it to. In this case, you could vent it to the atmosphere. And so what I want to do is remember one of the points of the mixture control is that it should compensate for altitude. All right. So as I go up in altitude, my potato chip bag here, I hope you don't mind me saying that because it seems to work in my head. The potato chip bag expands. And as this expands, it's going to drive this needle down. And I don't have the rest of this. And so what that's going to do is block off a passage and make it go richer. Now, what that passage could be whatever you want it to. In this case, it's probably going to block off a back suction or a bleed of some sort. But the whole point of what this slide is, I want you to see that it's a bellows, a sealed bellows. This represents a spring that is pushing it back up so that it always wants to be up, but the pressure outside gets less. Pressure in here expands against it and pushes down on this little pencil or pin, if you will. So, all right, so now let's see how it actually works inside of something. So here what we have is actually just a very basic carburetor. And we can now identify the float bowl without the float and the main metering jet because it says so, and the discharge nozzle. But this is going to use a back suction. All right. So right here where there's a massive amount of suction, they're going to plumb a vacuum to it. And so we can make a color here, which I've been using green because we could see. So we have a vacuum coming in here. All right. And that vacuum wants to lower the pressure here. And if it lowers the pressure here, that means that the difference between here and here becomes closer and closer together. And when these two equal the same, fuel stops flowing. So we keep that in mind. But over here, we have a passage that satisfies the need. Oops, what colors? Oh, I used blue for vacuum last time. That was my problem. Trying to be consistent. Blue is vacuum. So we have vacuum coming in here, and I said green was my pressure since we could see it. So over here we have ambient pressure, and it finds its way in here and fills all this up, and it supplies enough air out this way that there is no vacuum whatsoever on the float chamber. So right now this thing is running full rich, no automatic mixture control. But as I go up in altitude, this automatic mixture is going to start expanding, and it's going to start closing off this hole. So as it starts closing off this hole, there's less and less ambient coming in. So it's restricted. And so what happens is that because of its, well, that was not fun. Because of its restriction, there we go. Because of its restriction, we start to get, let's erase everything. We start to get inside of the float chamber more of a suction. So there becomes, since this starts to get a little bit of suction, it becomes more like the pressure right here. Not all the way, of course, because that would shut it down. But if this is more like this, then we get less discharge. So this just closes down the ambient coming in and doesn't supply enough, so the pressure drops in here. And if you think about it, and hopefully you do, you're going to notice that that is the exact same concept as the Stromberg mixture. Exactly the same. If I go back, find that one, you see.
So Kevin.
Yeah.
So there's nothing really automatic. It's mechanically, right?
No. Okay, this was the exact same concept, right? We had ambient coming in, and it supplied enough over here to meet the needs here until we started restricting the ambient coming in, and then we have a little suction that starts pulling over here, right? You remember that? It's the exact same thing. Okay, so now we'll go back here.
But instead of an economizer, we're talking about the mixture control, right?
Exactly. So it's, well, no. So on the Stromberg, that was a mixture. And this is also a mixture. So we're talking strictly mixture, not economizer.
This one's just automatic.
This one works exactly, you're right. It works exactly like the Stromberg, except the Stromberg, this up here was attached to an arm that went into the cockpit. And so I would pull it, and in effect, it would push this down. It doesn't, it's discs, but it would pull and push this down. And so push it, it would go up, pull, go down. That's how it would work. But this one is it goes up in altitude. This expands automatically and restricts some of the ambient coming in and automatically leans it out. Automatic mixture, not economizer, because now, too many things in my head. It's not an economizer, it's a mixture control. Now, if I wanted to make it an economizer, and this might, if you don't understand this, just kind of go, whoa, okay, don't worry about it. All I have to do is plumb this instead of the atmosphere over to here, to the manifold pressure. So if this is plumbed to manifold pressure, then it acts more like an economizer because it's based not on the atmosphere around us, but manifold pressure. So it will work on the ground, it will work at altitude, does everything. As where this thing here, all it's trying to do is figure out how high the aircraft is. That's what makes it a mixture, because it's trying to figure out where in the altitude world is the aircraft. As it goes up in altitude, this expands and does his thing. It does not care what position this throttle is in. That's why it's not an economizer, because it doesn't know and it doesn't care what's going on over here at all. Does not matter to it. Only outside air pressure. If
So
it was
is it-
somehow related to this, then it becomes an economizer, but it's not.
So this system is more accurate then
More accurate than what?
than the other one.
The economizer?
Yeah.
Okay, remember, an economizer is a completely different function. An economizer is built black. An economizer is built so that the rich lean curve looks like this. That's more accurate. All right. So it gets lean here and rich here based strictly on RPM. Okay. An automatic mixture does this. Goes lean, lean, rich, based strictly off altitude. That's all it cares about. So this one here is RPM. This one here is altitude. So this is a mixture, or AMC. AMC.
Wait, don't you want it backwards where it's rich on the ground and lean in the altitude?
Oh, yeah, I'm sorry. Wow. Thank you for pointing that out. So rich, lean. Thank you. So rich at low altitude, and honestly, it's leaning it out. But if we were to look at it, I change color so it doesn't look so bad. If we were to think about it, let's just say right here, it's 12-1. What should it be up here?
Still 12-1?
You got it, 12-1. That's the mixture I'm looking for. But remember, it gets complicated because that 12-1 is by weight, not volume. If I'm going to look at volume, it's going to be completely different. By the time we get up here, the volume is going to be much, much different. It's going to be, oh shoot, it'd probably be like, I don't know, 15, 16-1 or something. You need by volume, because you need a lot more air because it's so, it's not very dense. So by volume, it completely changes. But by weight, you're trying to keep it the same all the way up. It's because the weight of the air changes so drastically up at altitude that you've got to lean it out because you just can't get that much weight through. So, all right. Questions on that one? Yeah.
Yeah. Well, my point was that's exactly what you're looking for, right? To maintain that.
Yes.
Yeah.
Yep.
So
But
that's
remember,
what's more
it's not
accurate.
an economizer. This is not an economizer because an economizer is strictly based on RPM. This is a mixture, which is strictly based on altitude and air density of the air coming in.
So in the AMC, there's no pilot controls in the cockpit.
Nope, that's the A part, automatic. No, I will tell you this, there is no such thing as a fully automatic carburetor. You just don't do that. What you do is you have an AMC on top of or in addition to a pilot controlled.
Is that just a safety?
Well, the pilot, you still want control of stuff. And in fact, they get a little more complicated. If you look at pressure carbs, you will when we get to that, but I don't get too much into this. They actually have auto lean, auto rich. So it gives you a range of the automatic mode. And then there's a manual mode. So like something like this would be tied into this. And then like what you would do is you would put one of the valve systems in too. So you could still do idle cutoff. You could still manually lean. So this will take care of like most of the job. And then you see the problem with something like this is if you're out flying around and you say, okay, well, I want to go, 25 degrees lean of peak. Well, this doesn't let you do anything. It's like, well, it's set. I'm sorry, bud, you got what you got. So you can't do that. So you always want to be able to have further adjustments.
So the other one overrides, the pilot overrides the.
To a point.
To a point.
But
Okay.
if this is engaged and you want to go richer than this is letting you, it's not going to let you because this is leaning it out. So you're kind of stuck there. All right, so that's AMC. Oh, I guess I could write some notes about that. Discard. All right, so where are my notes around here? Marble shoveler. I'll get to that. All right, so I'm gonna, so I can keep kind of with where I'm at, I'll write notes right here. So V, way out V, way out. So idle cutoff, idle cut off, idle cutoff, or also called ICO. So, and the manual actually called that ICO. What the heck is that? Okay, idle cutoff. It is the position in which the mixture control, that's the red knob, shuts off all fuel to the engine. And I'm going to tattle on Katie because when you're flying and you're coming into land, so my procedure is I'm on downwind. So we've got the airport right here. This is the runway. And so so you take off and you're going to fly upwind, crosswind, downwind. So when the airplane is right here, I beam the numbers, I pull on carburetor heat, and I do a power reduction, and I start my glide, and I go base and final. So always right about here, when Katie's flying and I'm teaching her, I say, okay, we're getting ready to do a power reduction. We pull carb heat so that we don't get carburetor ice. So I say carb heat, and for the first, I don't know how many times, she would reach over and grab the red knob. And when you reach over and grab the carburetor heat and pull it all the way out, you'll see a power reduction because you just added carburetor heat, which means hot air, which means less dense air, which means that the mixture just got a lot richer. So you're going to see a power reduction, and plus the air isn't as dense. So you'll see a power reduction. That's how you know it's working. If you reach over and pull the red knob all the way out, you see a much bigger power reduction. It goes to 0 because you just shut the fuel off. And so she would inevitably every time reach over to start to grab that red knob. Mind you, I'm in a traffic pattern 1,000 feet off the ground, and the last thing I want to do is shut my engine off at that very point. But yet she would insist on doing it like all the time, and I would yell a little bit. I'm like, no, not the red knob. So red knob turns off the engine. No. All right. Poor Katie. All right.
That'd be pretty bad if she pulled that one out.
Well, you just push it back in. The engine should theoretically start, but should and theoretically are two things I don't want to deal with at that point. All right. So position which the mixture control shuts off all fuel to the engine. Well, that's actually how we want to shut down aircraft engines. We don't use the key. So it's safer to use than the ignition. Primarily because, oh good, all the fuel is used up. You don't have any fuel in the cylinders ready to fire off. So I guess I'm gonna write that. No unburnt fuel in the cylinders. All right, and that means also no risk of kickback. That's when the prop actually turns backwards. When ignition is turned off, turned off. Kickback is a huge deal, especially in Continental engines. They use a 90-degree drive starter adapter with washing machine technology. And I kid you not, back when I was young and poor and our washing machine broke, I took apart the transmission to fix it and realized that there was almost quite literally the same parts involved as the 90-degree drive in a Continental engine. It uses a spring that winds up around a clutch, and that spring will actually explode out into the engine. And that is a very, very bad day for, well, not the pilot. I mean, not the mechanic. You get a lot of work. So, okay, so safer to use ignition. I will tell you this though, if you have a Stromberg, there is no idle cutoff, right? Because I told you that the Stromberg The Stromberg carburetor does not have a usable idle cutoff. And I explained in great detail why that is. I'll just bring this over so you can remember the picture. Remember, because when this is closed right here, there is, all of this is yellow. And so you can mess with the mixture all day long and it doesn't do anything. It's messed up my drawing. There we go. Fix it. Okay. All right. And okay, what else does the idle cutoff do? Well, it allows pilot, if they're paying attention, and mechanic to check idle mixture. And you should see about a 50 RPM rise. So I take it down to an idle and I pull back the mixture and I should see the RPM gauge go from, I don't know, 700, 750, and then a sudden dive. Now, if you have the idle, if you advance the throttle and you have it running around 1200 RPM and you pull the mixture back, you're not going to see that rise probably because you're not in the idle circuit. You're off idle at that point. So, all right. Automatic mixture. Right, and I think I explained the idle mixture, idle rise, hopefully well at this point, that you fully understand that. So I didn't want to keep going with that. So automatic mixture. So automatic mixture, we'll say control or AMC. All right, with the use of a bellows, all three types of mixture controls can be automatic. Well, I don't know about three. We can just say all types of mixture controls can be automatic. Can be automatic. All right, so as altitude increases, the bellows expands. And as altitude, and it doesn't have to be just altitude, or absolute altitude above sea level. It could also be its density. It works for density altitude. So if I'm at McClellan at 70 feet, but it's 110 degrees outside, that's like about a 3,000 foot density altitude. And so my airplane thinks it's at 3,000, well, everybody's airplane thinks it's at 3,000 feet right there, unless you have a turbocharger. And so that automatic mixture is actually going to see that, and it's going to adjust for that. So as altitude decreases, pressure in the bellows, pressure, I just want to say causes bellows to contract. Bellows to contract. And I've showed you how that works. So you just use those to control a port, however you want to control it. Yeah, you can use it to control all kinds of things. You can use it to control a needle, a valve, air valve, fluid flow, anything you want to. It's however it's set up. And we're going to see different examples of that as we go through different carburetors. So usually, and when I write usually, it means almost always, usually used in conjunction with a manual mixture control.
I was just about to ask that on a if it's not a manual mixture control, and like if the bellow expands, how would it act? Like how would it? I guess the way to put the question is, would it go back to the pilot himself? Would he notice a change based on the contraction or expansion? Does that kind of make sense?
No, it did not make sense. I do not understand.
Okay, let me think about it.
Maybe write it in the notes. Write it in the chat. Okay. There's always going to be with the FAA questions about what happens if the manual mixture control breaks. And I love these questions because they're a give me question. You never really have to think much about them. We shouldn't have to. Slideshow. So what happens if this automatic mixture control gets a hole in it? Well, it doesn't work. And if it doesn't work, then the carburetor just works like it was never there to begin with. So what happens if you go up to altitude and the automatic mixture control stops working? Well, carburetor's going to run rich, right? Because that's just what they all do when they go to altitude. Now, where it gets tricky is if they say something like it sticks. So if the automatic mixture control sticks in the expanded position at altitude, and then you're coming down, what happens? Well, you just kind of think it's going to get lean. You're going to run lean when you get low, right?
Will it run lean enough to kill the engine?
I don't think so. No, I don't think so. That's my opinion. Stephen asks, when the bellows expands or contracts on an automatic mixture control and it's running lean and the bellows stays open like the bellows socks. Sticks. Sticks, yeah. Well, I think I just talked about that. So if you go up to altitude and it expands, the carburetor is running normal. It's actually running normal. That's its job. So it made it run closer to best mixture. And then you come down and the air gets thicker and you're not giving as much fuel, then it's going to run lean. If you're on the ground and it sticks and it sticks open and you climb, then it's just going to run rich when you get it to altitude. So it's if it breaks either on
So
the
it's
ground
better to
going
have
up.
it stick open.
What's that?
I said it's basically better to, if it breaks, you want it to break open, so it runs rich the whole time.
Sure. Yeah. Then you just use the manual mixture control, and now you're just like everybody else. So. All right. That really explains most of the carburetors and the systems, and we've pretty much been now through the whole thing. And the only thing that would really be left for you, well, we can look at some more pictures here, I guess, just because we can. And what we'll do next is we're just going to go over some carb advantages, disadvantages, and some repair notes, and just talk about them a little bit. But we'll look at some of these pictures here and make sure I covered all this. So again, this is our marvelous shoveler carburetor and some points to it. There's so much that you're gonna learn in lab, but there's stuff you won't. For example, I'm going to have you do airworthiness directives on these carburetors, and you will see in my notes that this is a very significant deal to me, that you cannot guess at parts, because for some reason when it comes to carburetors, people were making guesses and going, well, it's been complied with. And I'm like, oh, no. Just like the Magneto project. This is kind of a tricky little thing right here. See those serrations? Those are called serrations. And it's funny, there's an airworthiness directive on Marvel shovelers that don't have the serrations. And what was happening is this arm would get loose and rotate while this part didn't. So you can imagine this is actually the part that's pinned to the throttle, to the, the actual butterfly. And if you move this and you don't move this, that means that's not moving. That was pretty serious. And so they came out with the product improvement with these serrations that had a absolute lock to it. Don't forget this right back here is the idle speed screw. It just provides a stop right here that keeps that open. This is a check valve, a one-way check valve for the accelerator pump over here. Let's see. This is all kind of stuff you've already seen. Fuel inlet comes through here. There's a screen that should be checked every 100 hours or annual. Goes past the needle valve when the float drops down. This is right here. You should know that this is the manual mixture control valve that's going into there. So the fuel is going to come through here, and then work its way around and up through to the discharge nozzle. This is the idle system. So the fuel is going to come up through here, comes into here, and this is the main discharge nozzle, and the actual main metering jet on this particular carburetor is built in to the main discharge nozzles. If you pull the main sometimes I'll do that to you guys. I'll tell you my secrets because you'll forget. So during an oral, I'll say, well, where's the main metering jet? And I don't know, you'll pull this thing out and set it aside, and you will look and look and look and look, and guess what? It's the end of this. So it's built into that. So if you take this out and turn it around, you're looking at it. It does have a double venturi on these. So a venturi here and a venturi here. Okay, so the fuel comes up through the main metering jet on this particular aircraft and carburetor. Then it goes into the idle metering jet, which is a tube that actually unscrews. And then up the idle tube. And then just like we've seen before, we've got 1, 2, 3 discharge nozzles. When these are down here, they actually act as air bleeds. So right now, only one of these would be acting as a nozzle, and the other 2 are acting as air bleeds. And then as this comes down and uncovers them, it covers one, I'm going to add a second jet of fuel, and down here, another jet. And so we have 3 jets. Right now, it'll be 2 air bleeds coming in. There's also an air bleed up in here that pulls air in.
Okay, what the top screw does just keep the idle mixture adjust.
This one?
Yeah.
Okay, that screw is actually just holding the cover plate.
The plate, yeah.
Yeah, that goes in that this is screwed into.
Okay.
Okay, main system. So again, this is the idle mixture sleeve that actually goes into this is just the valve. So the fuel comes through here, goes through the valve, assuming it's open, up through here, and main discharge nozzle and out. There's an AD on these carburetors. This middle venturi was actually getting loose and getting sucked into the engine. And so they were a 2-piece. This is a small piece that sit in, and the big one would sit on top of it. But this is kind of weird. So they were getting loose and getting actually sucked into the engine. The engine was burning them. So, and then the engine would quit. And so you would think, and Marvel's answer was, okay, so let's just not make them in 2-piece. We know how to make this piece. We know how to make that piece. And instead of making them in 2 pieces, we'll just make them in 1 piece. And to me, that's just, okay, that's a no-brainer. But do you know they could not get these carburetors to work right for years after that? Absolute years. They tried changing the design of this nozzle. They had one that was open on the top. Then they had one that was called a salt pepper shaker that had holes here. And it got so bad that a lot of the guys out there and gals were actually going around to repair shops asking if any of us had any of these old 2-piece venturis laying around anywhere, because the airworthiness directive allowed you to still use them, but you had to do, I think it was every 100 hours you had to go in and take the whole carburetor apart and make sure that the venturis weren't loose. And they were far more happy to do that than to run this single piece that just would not allow their engine to run very well. It was really weird. And so, I mean, it was years and years until they finally kind of made it work right. And it's just so strange that that happened. But there's a lot of little nuances about these things that, we take for granted. I was talking with one of the old professors that was at City College, Kit Sodergren, who's an incredibly bright guy. And he gets into these nuances. He's actually super bright. And he brought one in, he was showing me how, like, it looked like they had a parting area or a little cast mark on it. He goes, you see that little casting mark? I'm like, yeah. And I'm thinking, I should have filed that off. He goes, that right there is designed to add this extra turbulence that comes right across here and does this weird thing. I'm like, wow. Like, how do you know that? So, all right, this is the accelerator pump. We're showing all of the little nuances of that. So this is actually the big one. So this is the MA6 carburetor. This up here is actually a needle valve that is going to control the pressure down on here. And so when you open the throttle up, this comes in and it hits that and it opens this up, and then it changes the pressure in here. So that's one of the more complicated needle types. So, but what I'm showing here is this is the accelerator pump, which is pretty much the same for all the Marvel carburetors. So when you pull back to idle, it pulls this cup up and it creates a suction in here. So it just draws fuel up here, past the little balls right there, fills this up. And at the same time, this is a check valve that goes out to the discharge nozzle. This doesn't go anywhere there. It looks like this because that's how they drill the passage. So can't make a drill go around the corner. So they drill it this way, then plug that and drill it down. So this is a check valve. So you pull it back, pulls fuel this way, but not this way because of this check valve. And when I accelerate, I push down. If I push down rapidly, it'll compress the spring, and then this will go down at sort of a reasonable rate. Blocks off here because of the check valve, comes up here, pushes this check valve open and sprays you in the face. And this is, this is the entire carburetor, kind of drawn out, but don't think I'm going to go through it. And that's just too difficult. But you guys will be using this drawing to get familiar with the carburetor and be able to explain it to me as we do our orals, which is really just everything we looked at, just kind of put together. And that's the big MA6 or 4 or 5, I should say. They go up to the 6, I think. So, all right. Back to some notes. Somebody's got to stop me about, actually, what time do we quit?
7:50.
All right. Then we're going to do this. Last thing. I got a little video for you.
Yeah, video.
Is that
All
a
right.
toilet?
Yes.
Oh boy.
Do you have sound?
No.
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 Let me see.
That's actually what I was going to refer to the float bowl. I just didn't ask.
Speakers, test speakers, switch to phone. Audio settings, audio.
That's a nice car.
Oh man, this is a
You
bummer.
put your speaker next to your microphone.
I don't think it is actually.
It is?
Okay, you didn't get any sound?
Oh no.
I can hear it through your mic.
Yeah.
I got audio.
All right.
Okay.
Looks like a Chevy.
I can kind of hear it.
Yeah, I can't hear it.
Oh, don't know what happened.
I mean, you can put captions on.
There's a way to make trips fun. Rather than focus on miles per gallon, think about gallons per hour. Because to me, burning a lot of gas for only a few minutes has got to be the same as burning a little bit of gas for a whole hour. Now, this is a carburetor. It controls how much gas goes into the engine. We're going to increase the capacity a little on this unit. Okay, when you look inside a carburetor, you'll see an open area here where the gas and air mix. And there's a reservoir, which is a small tank with a float in it that opens a valve and lets the gas flow. Does that remind you of something? The toilet drain is a little large for the intake manifold, but these toilet...
Sorry, I keep hitting buttons on my other screen so I can do stuff, and it does that.
gaskets are pretty flexible. Made out of beeswax, so real easy to work with. If you're a bee. I had to increase the size of the gas line to my new porcelain carburetor, so I went with 3/4 inch copper. My wife always says, go with the flow. I will. Now, to control the whole unit, I ran a piece of wire from the flush handle down through the firewall, hooked it onto the top edge of my gas pedal. So if you find she's idling too fast, just jiggle the handle. Pretty sharp looking, isn't it? I call it a Kaibo charger. I just hooked up the fuel pump and I'm waiting for the tank to fill up. Okay, they say the proof of the pudding is in the eating. Maybe that's not the best analogy. Hey, wait a minute. This is a man's car. Remember, when they don't find you, they should at least find it handy. And they'll find me gone.
All right. And on that disappointment,
At least the duct tape work.
remember, if the women don't find you handsome, they should at least find you handy. That's what he said. All right. Well, I'll see you guys tomorrow.
Alrighty, take care, Kevin.
All right.
Anybody
Kevin.
need the notes up?
Thanks for the knowledge, Kevin.
You got
Thank
it.
you. Thank you. Bye.